So when we say calorimeter, please, it is different from colorimeter. Their names are similar, but they are different. Calorimeter is a cylindrical vessel and is typically made of thin copper sheets. It is used to measure the heat energy of its contents. So the calorimeter is a device that is used to measure heat energy. As simple as that. The inner and outer parts are polished to minimize heat loss due to radiation. As you can see, this copper cylinder, you can see that this vessel is polished. That is why it's shining. The calorimeter is placed inside a rectangular wooden box, as you can see here, and it has a lid that slides into place. The lid also has an opening at the top, and that opening is placed there to allow the introduction of a stirrer and a thermometer. So the stirrer is used to mix the contents, while the thermometer measures the initial and final temperatures. Why wooden box and lid are used is because they are good insulators of heat. It means that they will trap heat and they will not allow heat to pass through the calorimeter. So that is why they are used. And the space between the calorimeter and the wooden box is filled with cotton wool. And cotton wool is also a poor conductor of heat. So all of this is to further reduce heat loss. Once again, I've already stated it before. I'm going to state it again that a calorimeter is a device that is used for measuring the heat flow or the heat energy. And it is used for calorimetry. Calorimeter is a device. Calorimetry is the technique. And you can define calorimetry as the technique or the process involved in measuring heat changes during chemical reactions and even during physical reactions. It could be during chemical reactions, it could be during physical changes, or basically you want to find out the heat capacity of a material. So the term calorimetry is divided into two. It's derived from two words, which are calorie and metry. Calorie is the amount of heat required to raise the temperature of 1 gram of water by 1 degree Celsius, and metry means measurement. So it's basically measuring the amount of water, the temperature of the water, the initial temperature of the water, and the final temperature of the water. So if you place something inside the calorimeter, that thing that you have placed or that substance, whether it's a chemical reaction or a physical substance, is going to transfer heat into water. And so the temperature of the water will increase. So with the increase in the temperature of water, you can use it to calculate the energy that has been transferred from what you have introduced into the calorimeter. That's the basic principle of the calorimeter. And so because when we talk about thermal equilibrium, you have to understand that heat will always flow from a hot region to a cooler region until there is a thermal equilibrium. That means the heat remains the same. So heat flow is always from hot to cold, not from cold to hot. You have to also take note of that, okay? Then lastly, heat energy can be measured in joules or in calories. Like I have said before, by nature, heat flows from a region of higher temperature to a lower one, to one of lower temperature within a system or a body. So that is all for introduction into calorimeter or calorimetry. The next lesson will be about the different types of calorimetry. Alright, so for calorimetry, there are three types of calorimetry. So we have the constant pressure calorimetry, the constant volume calorimetry, and the differential scanning calorimetry. You have to take note of those three types of calorimetry because definitely it will come out in your exams. And then an easy way to remember the constant pressure calorimeter, that is the first one. Well, imagine you have two coffee cups and you use one as the base and the other as a loose fitting lid. And so since the top coffee cup is not tightly sealed, the calorimeter operates at the constant pressure of the atmosphere. So if I ask you why this calorimeter is operating at the constant pressure of the atmosphere, you will tell me it's because the top coffee cup is not tightly sealed. So it is sometimes called the coffee cup calorimeter. I can also ask you what type of calorimeter is called the coffee cup calorimeter. That is the constant pressure calorimeter. So constant pressure calorimetry involves measuring heat flow. And other components of this calorimeter include the coffee cups, apart from the coffee cups, some water, a stir bar, and a thermometer. Now look at this example. Supposing we have 150 grams of water at an initial temperature of 25 degrees Celsius placed inside this coffee cup calorimeter. And then we also added copper, the substance, copper substance or a copper sample of 120 grams. But we make sure we heat that copper sample to 100 degrees Celsius. If you add it into the calorimeter, you know that the copper is at a higher temperature, so heat will flow from the copper to the water. And when that happens, when you use the thermometer to measure the water, the initial temperature of the water was 25 degrees Celsius. It has now increased rather to 30 degrees Celsius. So to calculate the heat gained by the water, we use this formula. Q is equals to mc delta T. Q is the heat gained by the water. M is the mass of the water. C is the specific heat capacity of water, which is 4.18 joules per grams degrees Celsius. And then the delta T is the change in temperature. Change in temperature is the final temperature minus the initial temperature. What was the initial temperature of the water? 25 degrees Celsius. What is the final temperature of the water? 30 degrees Celsius. So you just simply do 30 minus 25, and that delta T is equal to 5 degrees Celsius. So when you place all of this into the formula, the mass of the water times the heat capacity times the temperature change, you are going to have plus 3.1 times 10 raised to power 3 joules as the heat energy gained by the water. I hope you understand. So that positive sign, why we're adding plus, is because it is gained. If it was minus, it's because it was lost. But because energy was gained by the water from the very hot copper substance, the copper was at 100 degrees Celsius. It was because the copper was very hot. It transferred its energy, because energy will always flow from a hot region to a cold region. And in this case, the hot region is the copper and the cold region was the water in the calorimeter. So that is why the temperature of the water increased from 25 degrees Celsius to 30 degrees Celsius. And so after calculating the heat energy, it was 3.1 times 10 raised to power 3 joules. Okay, so please take note of all of this. I might ask you some questions. I might ask you, what is the meaning of M? What is the meaning of delta T? What's the meaning of Q? What is the specific heat capacity of water? It can be 4.18, approximately 4.2. Any one of those is correct. So please take note of all of this for the sake of your exam. And then the next is to calculate the energy lost by the copper. We also use the same formula, but the only difference is that the copper, the specific heat capacity for copper is 0.39 joules per grams degrees Celsius. And of course, the heat lost, the temperature rather, change in copper. The final temperature is 30 degrees Celsius. Both of them, I spoke about thermal equilibrium. So that 30 degrees Celsius is not just for the water, it's also for the copper, because it will always flow from the higher region to the lower region until there's a thermal equilibrium. So initially, the temperature of the water was 25 degrees Celsius and the temperature of the copper was 100 degrees Celsius. But because of that physical change, they both achieve a thermal equilibrium of 30 degrees Celsius. So 30 degrees Celsius is the final temperature of the copper minus the initial temperature, which was 100 degrees Celsius. So we have a negative value of minus 70 degrees Celsius. So when you add that into this calculation, we have the mass of the copper as 120 grams times the specific heat capacity of copper times the temperature change, which is minus 70 degrees Celsius. You are going to have minus 3.3 times 10 raised to the power 3. If positive means heat gained, minus will mean heat lost. So that means that the copper lost this energy to the water. But when we bring two of them side by side, the two answers, we discover that one is plus, right? One is plus 3.1 times 10 raised to power 3 joules, but the other one is minus. They are not the same. If they were both plus 3.1 and the other one was minus 3.1, that is, they were both 3.1, we would have said, okay, it was the same values. Minus and plus cancel each other. But because we have minus 3.3, it means that the energy that was lost to the water by the copper was not 100%. That means that some of the energy was lost to the surroundings. So some heat was lost to the surroundings. So it was not a perfect energy transfer. If no heat was lost, like I'm reading from the material now, if no heat was lost, the values would have remained equal. That means we would have had plus 3.1 and minus 3.1 times 10 raised to the power 3 joules. Do you understand? So that is energy using the constant pressure calorimeter in a physical reaction. But what about in the case of a chemical reaction? So for a chemical reaction, the reactant and the product, let's say you are dissolving sodium in water. That becomes the reactant and the product. You know it's going to release hydrogen gas and sodium hydroxide, if you remember your chemistry class. So that would mean that the reactant and the products, in that case the sodium and the water, form the system. That is the system. While the surroundings, the water, the coffee cup, the thermometer, and the external environment is the surrounding. So the surrounding and the system makes up the universe in that context. So if I say, what is the universe? You tell me the universe includes the surrounding and the system. If I say, what is the system includes the product and the reactants. If I say, what is the universe includes everything. That means the surrounding, including the system. Remember, the surrounding itself is everything in the calorimeter, the coffee cup, the thermometer, the stirrer, the water, the reactant. No, apart from the reactant of the product, sorry, just the external environment. So in an exothermic reaction, when we say exothermic, that means heat will be released into the atmosphere. And this is what will raise the temperature of the water. Just like that hot copper raised the temperature of water. But because it's a chemical reaction and it is exothermic, the temperature of the water will be increased. We also use the same formula as Q is equals to MC delta T to calculate the energy that has been transferred from the reaction because it was exothermic to the water. And we'll also get our values. And we'll also know or calculate the energy that was lost by the reaction. So we also do the same for endothermic reaction. But for endothermic reaction, since energy is being gained from the environment, it means that the temperature of the water will even be reduced. And so that will give us a negative value. So that's the for chemical reaction. Then the last, I'm not going to talk about the differential scanning calorimetry. You can read up on that if you want to, but it's not that necessary for the course of this work. So the constant volume calorimetry is used to measure the heat of reaction while maintaining a constant volume, even under conditions of high pressure. That's why it's called constant volume calorimetry. And this is the way it looks like. These are some of the apparatus or things or components of the constant volume calorimetry. Why these are some of the components of the differential scanning calorimetry. So that's the end of this class. All right, so the chromatography is a technique that is used to separate different molecules in a pigment. Ink, your pen ink can be a pigment, for example. Chlorophyll, the leaf, can be a pigment. There are different molecules that make up this pigment, but you will not notice because the color is the same. When you look at your pen ink, it could either be black, blue, or red, or whatever the color may be. But the truth is that there are different molecules in that mixture. So that pigment is actually a mixture of different molecules. And the only way you can separate it to see that there are different colors that make up that particular uniform pigment is using this device called or technique rather called chromatography, because we have different types of chromatography. So the term chroma means color and graphy means to write. And it was invented by this man in the year 1901. I cannot pronounce his name, Michael Tesvet or something. So in the year 1901, he was the one that invented the chromatography. How did he do this? He filled a column with calcium carbonate and he added leaf extract along with a mixture of ether ethanol. So the ether ethanol was a liquid. Please take note of the liquid, take note of the sample, take note of the liquid, take note of the solid. The sample was the leaf extract. The solid was the calcium carbonate. The liquid was the ethyl ethanol. So he discovered something. He discovered that as the leaf extract passed through the column, the chlorophyll, that is the green pigments in the leaf extract, were separated. They separated into different colors. Like I earlier said in my introduction, just one green color was separating into different colors. So he understood that, oh, there are other molecules inside this particular chlorophyll pigment. So the calcium carbonate that is packed in the column is referred to as the stationary phase. The stationary phase is the solid. Remember I told you to take note of the solid. That calcium carbonate is the stationary phase. So in my exam, if I'm asking you, according to the first chromatography experiment, what was the stationary phase? Your answer would be calcium carbonate. So why the ethyl ethanol mixture is the mobile phase. The mobile phase is also called the liquid phase. So the liquid phase is the ethyl ethanol. Please take note. The mobile phase will move down the column along with the sample, which is the leaf extract. And so that leaf extract is called the analyte. The sample is called the analyte. So the colorful separation of the chlorophyll pigment in this process is called the chromatogram. All the separation, all the pigments, all the different molecules aligned. It's just like forming a rainbow of colors from that one green pigment is called the chromatogram. And so these are some of the terms that we use in chromatography. The eluent. The eluent is the mobile phase that you introduce into the column. Remember we said the mobile phase is the liquid phase, but now we're having eluent. As you are introducing it into the column, that ethyl ethanol is called eluent. But once it starts coming out of the column, it's no longer eluent, it becomes number 2, eluate. So the eluate is the mobile phase. It's also the mobile phase coming out or leaving the column. So both eluents, that is number 1 and number 2, are both mobile phases, or are both the mobile phase. The difference is that one is entering and the other one is leaving. It's just like you are a student now. You were coming in as you can either be an incoming student or an outgoing student or a graduating student or whatsoever the case may be. So there are different types of students. There are undergraduates and there are graduates or graduating since you are still in the process. But the eluent is the mobile phase that is coming in, and the eluate, the one that has ATE at the end, is the one that is coming out. Then the eluite, the one that has ITE, that is number 3, is the sample that is coming out from the column. The sample coming out from the column is the eluite. So when the leaf extract is applied to a column, the chlorophyll pigment, the first thing that you need to take note is that the sample is the leaf extract. The moment you pour it into the column, the first thing that you take note is that the pigment is absorbed by the stationary phase. That is the solid phase. The calcium carbonate will first of all absorb the leaf extract. Then when you pour the mobile phase into the column, the chlorophyll molecules that are most soluble in that ethyl ethanol, which is the mobile phase, they will begin to move faster as you are coming down the as it's flowing down. It will move faster, while the less soluble molecules will move very slower or slowly. And as that is happening, there will be different molecules or different colors that will be formed on the mobile phase, on the solid phase rather, stationary phase. You will see it clearly, different colors. So we say that the color or the separation rather occurs due to the differential partitioning of the sample between the mobile phase and the stationary phase. So we have different types of chromatography. I gave you 7 here. We have the paper chromatography. I don't need to read them out. So just read them yourself. Read the different uses. You need to know what paper chromatography is used for. You need to know what the thin layer chromatography is used for. You need to know their names. I can give you different examples and types and ask you which one is not a type of chromatography. That can be an exam question. I can mix them up. I can tell you what is the full name of GC, what's the full name of TLC. That is number 2. You can see number 6 is HPLC. What is the full meaning? What is the difference between LPLC and HPLC in terms of sensitivity? You can see that the LPLC is less sensitive than the HPLC. So all these are the things you need to take note of. When you are reading my course, you have to take note of write all the key facts, write all the definitions, and you need to ask yourself, okay, why is this one different from this one? How is this one similar to this one? You have to take note of the differences and the similarities. So I wish you the best in your exams. Thank you.